All right, let's take a look at our fourth example from chapter 1. In 1656, Otto von Guericke of Magdeburg presented his invention, a vacuum pump, through a demonstration that became a popular sensation. A metal sphere made of two hemispheres, known as the Magdeburg hemispheres, was evacuated so that a vacuum would hold the two pieces together. Van Guericke would then have several horses, by one account 30 of them in two teams of 15, pulling unsuccessfully to separate the hemispheres. The demonstration would end with the opening of a valve that removed the vacuum and allowed the hemispheres to separate. Suppose that the diameter of the sphere is 50 centimeters and the sphere is completely evacuated. The sphere is hung from the ceiling and you pull the other half with the force of your body weight. Will the hemispheres come apart? Support your answer with calculations. Hey, cool. All right. So we have a sphere that's been evacuated. So the pressure inside the sphere is zero. So the key to remember is if I first let's think about the force acting on that sphere to hold it together. So pressure, remember, is force per unit area. Right? So pressure, right, is my force per unit area. So in this case, if I want to get an idea of the force holding those two spheres together, okay, I'm going to write it as the force holding my two spheres together is equal to, I'm going to write it as delta P being atmospheric pressure relative to the evacuated sphere, which is a pressure of 0. So it's really P, but I'm going to write it as delta P times A. Okay. All right, well, what is A? Okay, well, for A, I'm going to need to look up the formula for the surface area of a sphere. Okay, so that's not in the appendix. I'm going to open up a new window. And so I'm going to look up the surface area of a sphere. So the surface area of a sphere, Google tells us the equation is 4 pi r squared. So A is equal to 4 pi r squared. We're given the diameter, all right, so I can write that as 4 pi d over 2 squared, or 4 pi, then 1/2 squared becomes 1/4 d squared. So I'll write this as pi d squared. All right, so surface area is 4 pi r squared. So I just replace r with diameter, which is d over 2. So d over 2 squared would be d squared over 2 squared. Right, where 2 squared is 4, would cancel with that 4. So the force, all right, holding my two spheres together then, is going to be equal to delta P times pi times d squared. All right, so let's calculate first the force holding those two spheres together. Okay. So the force is equal to, okay, well, so we know we're told D is equal to 50 centimeters. Okay, now delta P, okay, so my sphere is evacuated. And so what I'm looking at, delta P, is my atmospheric pressure relative to that pressure of the vacuum. So delta P, I'll write is 1 atm. Okay, what is 1 atm? Okay, well, so now let me close this. So we're in the appendix. Okay. Chapter 1, they had it written out better. Come on, do they have it in here? Yeah, so 1 atm is 1.013 times 10 to the 5 pascals. So that's 1.013 times 10 to the 5 pascals. Okay, so pascal's my SI unit. Okay, and so in terms of Pascal, okay, remember Pascal is force per unit area, so that has units of newtons per meter squared. So I'm going to write this as 1.013 times 10 to the 5 newtons per meter squared. Okay, so isn't even a need for a conversion factor since it's just 1 atm, which is equivalent to this. So my force then, okay, is equal to 1.013 times 10 to the 5 newtons per meter squared times pi times my diameter squared, which is 50 centimeters. Okay. Okay, and so it's going to be 50 centimeters. Okay, before I square it though, I'm going to convert from centimeters to meter. All right, and so I know that 1 meter is 100 centimeters. All right, and then I'll square that. So once I convert my diameter to meter, then I'll square it. And that should give me a force in newtons. Okay, so my force, okay, so let's go over here. So this is example 3. So pressure in nm cubed, right? Newtons per meter cubed is 1.013 e to the 5. Okay. Cool. My diameter in centimeters was equal to 50. And then meters to centimeter, right? My conversion factor is just 100. So my force on the sphere in newtons is equal to my pressure in newtons per meter cubed times pi times, okay, in parentheses I'll have my diameter divided by my conversion factor for meters to centimeters, and then that squared. And actually does that, it's newtons per meter squared, right? So I had it right there. Just didn't say it right here. All right, so if I save that and run, get into error because I didn't update it there. Let's see, so got a typo. So this is my pressure in newtons per meter squared. Oh, I've got that misspelled. P underscore N under M2 times pi times D underscore CM, which is my diameter in centimeters. So my force is 7.9561 times 10 to the 4. So the force acting on the sphere to hold it together is equal to 7.9561 times 10 to the 4 newtons. Okay. So now the question is, or the problem asks, is if I were to, grab on to one of the spheres, right? So if it's hanging from my ceiling and I have, say, a little hook that I can grab onto to hang from the sphere, is the weight of my body enough to separate the spheres? That's the question. And so this is, meant to give you an idea of, how strong, right, one bar is, right? Kind of give you a feel for unit of pressure. Okay, so if I'm hanging, right, then I'm going to exert a force due to gravity. So the force I can exert is what? Okay, well, I know the force due to gravity, my force due to gravity of grabbing onto the sphere and hanging would be equal to what? Well, my force is just my mass times acceleration, which in this case is my mass times g, my gravitational constant. Okay, where g, okay, we're sticking with SI units, is 9.81 meters per second squared. Okay, and mass, how much does an average person weigh? I don't know. Just to say conservatively, let's call it 150 kilograms. So the force, that a 150 kilogram person would exert would just be equal to 150 times 9.81 meters per second squared, and that would be equal to RSFG of person. So mass in kilograms, right? We said let's just assume it's 150, and then G in meters per second squared is 9.81. Okay, so the force due to gravity, which would also be in newtons, is equal to mass in SI units times my gravitational constant, also in SI units. So 150-pound person would exert a force of 1.4715 newtons. So no, all right, so that force that person could exert is 1.4715 times 10 to the 3 newtons. All right, so a 150-pound person is off by an order of magnitude. So what that would tell me then is I would need to weigh, say 10 times more. So it'd be a 1,500 kilogram person. Okay, so a person though, would the force due to gravity they would exert would be 1.4715 times 10 to the 3 newtons, which is much less than the force acting to hold those spheres together. So one person could hang from that sphere without separating. Okay. Pretty cool, all right? And so that's a sphere with a diameter of 50 centimeters. So if you had a 50 centimeter diameter sphere and evacuated it, then you could hang from it without pulling those two halves apart. All right, cool. All right, that's the end of our Chapter 1 examples. We'll see you in Chapter 2.